This is Physical Science 20 Waves. This is the PowerPoint that goes along with the assignment W3, Speed and the Universal Wave Equation. The first formula is one that you used in grade 10. It's used for calculating speed. And your speed depends on two things: how far you've traveled and how long it took for you to travel that distance. So the speed of an object depends on how far the object has traveled in a given amount of time. I want you to add these notes to your pink sheet, that v is speed measured in meters per second, d is distance measured in meters, and t is time measured in seconds. The second formula is known as the universal wave equation. The speed of a wave depends on two factors. It is found by multiplying the length of the wave by how many waves are produced each second. V is speed measured in meters per second. Wavelength is symbolized by the Greek symbol lambda, and is measured in meters, and frequency is symbolized by a small f, and it's measured in hertz. Mechanical waves can have different speeds. The speed of a wave in water depends on the water's depth. Waves travel faster in deeper water. The speed of a wave in a slinky depends on the slinky's tension. In class, we would have had two students pull a slinky as far apart as they can, without damaging the slinky. And when one student sent a wave down, we would see that the wave travels very quickly through the slinky. Then when the two students come closer together, the tension would be less, and when we see a student send a wave through the slinky, we would see that that wave would travel much slower. Sound is a wave, and the speed at which sound travels depends on the temperature of the air. The graph below shows us as the temperature of the air increases, the speed of sound also increases. The speed of a wave is not affected by the wave's amplitude, wavelength, or frequency. We said that the speed of a wave in water depends on the depth of the water. So in both situations we see here, taken on two different days, the speed of the waves passing this boat are the same. If we look on the left, there's a small wavelength. And if wavelength goes down, that means that frequency has to go up, because when the two numbers are multiplied together, they have to equal v, and v does not change. So if you've been on a boat when there are small waves, you know that the waves are hitting the side of your boat quite quickly. On the right-hand side is a day when it's windier and the waves have gotten bigger. The waves are longer. The wavelength has increased. Since v cannot change, if wavelength goes up, then frequency has to go down. And you have noticed this if you were on a boat as well out in the lake on a windy day when you have large waves, and the waves slowly crash up against this side of your boat. When a wave hits a boundary, it may continue into the new medium, be reflected back, or may do both, as part of the energy may be reflected while the remainder is transmitted. One can determine the amount of energy transmitted by the mechanical wave through the difference in amplitude between the incident and reflected wave. When the wave is coming in, 100% of its energy will hit the boundary. If we note that 40% has been reflected back, it can be concluded that 60% must have been transmitted into the new medium. The reflected wave will either be erect or inverted. Hitting a denser medium or a fixed end will create a reflected wave that is inverted. So if I'm sending a pulse down a slinky, if the person on the other end is holding that end tightly, that wave will come back inverted. Hitting a less dense medium or a loose end will create a wave that is erect. So if the person I'm sending the wave down to is very weak and has a spaghetti arm, when I send that wave down, I might throw their arm around and the wave would come back on the same side. The transmitted wave has the same frequency as the incident wave, but the change in density means the speed of the wave must change. How is this possible? The speed of a wave will change, as will the wavelength. The increased speed means a longer wavelength. The decrease in speed means the wave now has a shorter wavelength. Going into a denser medium causes a decrease in speed. Think of it as running into water from the beach. You slow down entering a denser medium. Both mediums in this graphic have the same frequency. If I'm holding onto the slinky at this end and I'm sending down 10 waves per second, that means that 10 waves per second are hitting this boundary, which means 10 waves per second are being transmitted into the new medium, which means whoever is on the other end of the slinky will be receiving 10 waves per second. So the frequency is the same throughout the entire slinky. We can see in the slinky that the wave is traveling faster on the left-hand side than it is on the right-hand side. The velocity in the less dense medium is equal to wavelength in the less dense medium multiplied by frequency in the less dense medium. The velocity of the wave in the more dense medium is equal to wavelength in the more dense medium multiplied by frequency in the more dense medium. The wave in the less dense medium is traveling faster. That means that the velocity in the less dense medium has increased. Since frequency cannot change, the only variable that can change on this side of the equation is wavelength. So if VL has increased, wavelength L has to increase as well. Just like on the opposite side, the velocity is slower in the more dense medium. So if velocity has decreased, this side of the equation must also decrease. And since frequency cannot change, it is a wavelength that must decrease. So if there is a change in velocity and frequency is fixed, that means the wavelength must have changed. One other note about this graphic, we have the incident wave coming from the less dense medium. What's going into the more dense medium we call the transmitted wave, and then we can see that part of the incident wave is reflected back. Since we're going from a less dense medium to something that is more dense, since it's going from a material that's easy to move to a material that is harder to move, it acts as a fixed end, and that reflected wave comes back inverted. Superposition of waves. When waves overlap, the resulting amplitude is the addition of both waves' amplitudes. What we see at the top is a wave that is traveling this direction. On the middle, we see a wave that is traveling this direction. And at the bottom, we see both those waves traveling through a slinky at the exact same time. Constructive interference happens when two waves meet on the same side. An example would be when two crests meet or two troughs meet. But both waves are on the same side of the rest position when they meet. In this case, the slinky traveling to the right is pulling the slinky up. The slinky traveling to the left is pulling the slinky up. And then in the slinky itself, we see an amplitude that is the addition of both amplitudes of the two waves that are traveling in that slinky. So if this is 2 units high, this is 2 units high, this would be a total of 4 units. Likewise, if the wave traveling right is pulling the slinky down, and the wave traveling left is pulling the slinky down, we will see the slinky getting pulled down. If this is pulling the slinky down by 2 units, and this is pulling the slinky down by 2 units, we will see the slinky being pulled down a total of 4 units. Constructive interference doesn't just happen at the crests and the troughs. It happens anywhere that the waves are pulling the material in the same direction. In this case, the wave traveling left is pulling the slinky up. The wave traveling right is pulling the slinky up. So the slinky is pulled up. And if this is a total of 1.5 units, and this is a total of 1.5 units, then the slinky is being pulled up a total of 3 units. In the exact same graphic, we see that there is not constructive interference everywhere. Because if I look at the wave traveling to the right, it is pulling the slinky up, but the wave traveling to the left is slightly pulling the slinky down. That means that they're going to partially cancel each other out. Destructive interference occurs when two waves meet on opposite sides of the rest position, like a crest meeting a trough. If I look at the wave traveling to the right, it is pulling the slinky down. If I look at the wave traveling to the left, it is pulling the slinky up. Let's say the wave traveling left is pulling the slinky down half a unit, while the wave traveling to the left is pulling the slinky up 1.5 units. That means that the overall slinky will be pulled up 1 unit. Here's the exact same graphic, and we're going to look at a spot on the slinky where the slinky is sitting at rest position. And that is because the wave traveling to the right is pulling the slinky down, the wave traveling to the left is pulling the slinky up, and they are pulling with the exact same magnitude, so they are canceling each other out 100%. And when they completely cancel each other out, and it results in the slinky being at rest position, we call that total destructive interference. Total destructive interference occurs when two waves meet. The crest is equal in size to the trough, causing the medium to be at rest. And if our waves are the exact same length and they have the exact same amplitude, when they meet on opposite sides, it will result in total destructive interference. And the slinky, for a split second, will appear to be completely flat. This is an animation you can check out if you want to. I put the web address at the bottom. It allows you to play with the amplitudes of two different waves and see what happens when they collide with one another. Mr. Sklar finished the Regina Queen City half marathon in 2 hours, 2 minutes and 14 seconds. That is my time. So in my variable list, I'm going to start by writing time. Time is 2 hours plus 2 minutes plus 14 seconds. But that is all going to have to be in seconds. So I'm going to have to switch hours to seconds, and I do that by multiplying by 62 times. 2 hours multiplied by 60 will give me a number of minutes. Multiplied by 60 again will give me the number of seconds. The 2 minutes will also have to be converted into seconds, so I will have to multiply the 2 minutes by 60, and then I will have to add the 14 seconds. So 2 times 60 gives me 7,200. 2 times 60 gives me 120. And then there's 14 more seconds, which will give me a total time of 7,334 seconds to complete the race. It says if the distance is 21.1 kilometers, that is going to be my distance, so D equals 21.1 kilometers. But distance is going to have to be in meters. Metric prefix K, kilo, means times 10 to the 3. So I can substitute in times 10 to the 3 for small k. Now my distance is in meters. And it asks me what was his average speed in meters per second and kilometers per hour. I'm looking for speed, and speed is symbolized by a v. So v is our unknown. The formula that has t, d, and v in it is v equals d over t. I'm looking for v. It's already isolated, so I can go directly into substituting numbers. So I'll put in 21.1 times 10 to the 3 meters on the top and 7,334 seconds on the bottom. Now I'll run that through my calculator. And that gives me 2.877 meters per second. 3 significant figures because I had my givens to the nearest second, which are 4 sig figs, and my distance was given to me with 3 significant figures. Now I need to convert that to kilometers per hour. Now at the bottom of the screen, I have a note that says magic number to convert between meters per second and kilometers per hour is 3.6. And a note that meters per second is always smaller. On your pink sheet, you may want to write kilometers per hour divided by 3.6 equals meters per second, and that meters per second times 3.6 equals kilometers per hour. So since I have meters per second, and I want to convert to kilometers per hour, I will multiply my answer by 3.6. I will multiply my pre-rounded number by 3.6, which luckily is still on the face of my calculator. So I will just multiply the answer on my calculator by 3.6. And that gives me to three significant figures 10.4 kilometers an hour. Example 2, with what frequency do waves, so I'm looking for frequency, F equals question mark. With what frequency do waves hit the side of the boat if the wavelength is determined to be 4.8 meters? So wavelength, lambda, equals 4.8 meters. And the waves are traveling 9.0 kilometers an hour. That's their speed. So V equals 9.0 kilometers per hour. But speed has to be in meters per second. In the previous example, we said that meters per second is always smaller and the magic number is 3.6. So I'm going to divide 9 by 3.6 to convert kilometers per hour to meters per second. So meters per second is 9 divided by 3.6. And that gives me exactly 2.5 meters per second. If it wasn't an exact number, I would have to make sure that I don't do any rounding until I'm done the question. Now, what formula has frequency, wavelength, and velocity? It was the second formula that we looked at the beginning of the lesson. Velocity equals frequency times wavelength. So velocity is the product of wavelength multiplied by frequency. I'm looking to get frequency by itself. It's not by itself. So in order to get wavelength away from frequency, I'm going to divide both sides by wavelength. So wavelength and a wavelength will factor out. And I now have F all by itself. F is equal to V divided by lambda. So F equals V divided by lambda. I have F by itself. I can now substitute in the numbers that I have in my variable list. V is equal to 2.5 meters per second. And on the bottom, I put lambda, which is 4.8 meters. Meters and meters will factor out. And that's going to give me seconds on the bottom. And we said that 1 over S is equal to hertz. So I wind up with 0.520833 hertz. Two significant figures because both numbers that I have been given have two significant figures and we had been dividing. Example 3. How long will it take a car to travel from Regina to Calgary? So I'm looking for time. It tells us the car is traveling the speed limit of 110 kilometers per hour. So that's my velocity. Velocity should be in meters per second, but if I read on, it says the entire trip is a distance of 759 kilometers, so that's distance. And it's asked me to give my answer in hours. So since I am in kilometers and hours, I will just leave my units as kilometers and kilometers per hour. So I've got T, V, and D. The formula that has those three variables is V equals D over T. I'm looking for T, but T has two problems. It's not by itself and it's in the denominator. So we said anytime we have a variable in the denominator, we want to get it into the numerator. So I'm going to multiply both sides by T. When I do that, both T's on the right-hand side will factor out. And I will now have TV equals D. Now I have T in the numerator. Now I can try to get T by itself. T is next to V, so I need to get rid of V. I have to move it away from T. So I'll divide both sides by V. Now on the left-hand side, I have a V on the top and a V on the bottom that will factor out. So now I have t by itself, and it is equal to d divided by v. Now that t has been isolated, I can substitute my numbers in. So I will substitute in 759 kilometers for distance, 110 kilometers per hour for velocity. And that gives me 6.9 hours. The kilometers factored out, I wound up with hours on the bottom of the bottom, and when I have something in the denominator of the denominator, that flips it 2 times, which puts it up into the numerator. Green light has a frequency of 588 terahertz. There's a note that you might want to add that big T is tera. It is a metric prefix that means 10 to the 12th. It is also our frequency. So I'll write frequency equals 588 terahertz. And I will substitute in for the big T times 10 to the 12th. So frequency is 588 times 10 to the 12 hertz. It says, what is the wavelength of light with this color? So I'm looking for wavelength. And we might think that's all we have in the variable list, but it told us this is green light. And since we know it is light, and light is an electromagnetic wave, we know that the speed has to be equal to c. So speed is equal to c, which is the speed of light, which is an electromagnetic wave, which is 3.00 times 10 to the 8 meters per second, and that number can be found on your pink sheet. Now I've got frequency, wavelength, and velocity, so I'm going to be using the second formula that we came across today, which is speed equals wavelength times frequency. I'm looking for wavelength. I have to get wavelength by itself, so I'm going to have to move f away from wavelength. So I'm going to divide both sides by f. So on the right hand side, I have an f on the top and an f on the bottom. They can factor out. So wavelength equals speed divided by frequency. Now that I have wavelength isolated, I can substitute my numbers in. Velocity on the top is 3.00 times 10 to the 8 meters per second, and frequency on the bottom is 588 times 10 to the 12 hertz. When I punch that into my calculator, that gives me 5.10204 times 10 to the negative 7 meters. How did I get meters? Well, a second on the bottom factors out with a second that is on the bottom of the bottom, leaving us with just a single m in the numerator. So my answer is 5.10 times 10 to the negative 7 meters, but it said answer in nanometers. So I will have to write this answer out of scientific notation. So that's 0.000000510 meters. I know that a nano, which is a small n, is a metric prefix that means times 10 to the negative 9. And that's something you can find on the data table on the pink sheet. So if I look here, I'm going from meters to nanometers. Nanometers is a smaller unit, and you may have heard me say that all conversions are BS. So if I'm going to a bigger unit, my number gets smaller. If I'm going to a smaller unit, my number gets bigger. I'm going to a smaller unit. I want to get to nano, so that means my number has to get bigger. So that means my decimal is going to be moving this way. It's going to be going over 9 spots. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So the decimal will have to go here in order for meters to become nanometers. So that gives me 510 nanometers. And I want to put the decimal in there because that 0 is significant. We need 3 significant figures in our answer. Last set of examples. Example 5. Miss Holshoff plucks a 65 centimeter long string 17 meters from the bottom of the string. Where will the pulses meet again? Well, the pulse is going to go to the left and to the right at the same time. They're also going to travel the exact same speed because it's the material that dictates how fast the wave travels. And they're both going to be traveling inside of the same string that she has plucked. So when she plucks the string, a vibration, like we said, is going to go left and one's going to go right. Once this wave hits here, it is going to become inverted because it has hit a fixed end. And then they're both going to continue traveling through the string. At this point, this wave has now hit a fixed end and it will also become inverted and it will bounce back. And those waves will then meet 17 centimeters from the other end of the string. The pulses will meet again 17 centimeters from the top of the string. The pulse was started when Miss Holshoff plucked the string 17 centimeters from the bottom. They will meet again 17 centimeters from the top of the string. When they meet, will they result in constructive or destructive or complete destructive interference? Well, they're going to meet and result in constructive interference because they are both inverted. They both started erect, they both hit the ends of a string, which inverted them, and when they both came back, they're both inverted, they're both pulling the string down, so it will be constructive interference. Will the waves be inverted or erect when they meet? They both hit a fixed end, which caused them to become inverted. You can now work on the W3 assignment.